So it's my pleasure to announce the second speaker of this last session, Sami Douba, and he will tell us about proper cat-zero actions of unipotent-free linear groups.
Thank you, Turbo, for the invitation to speak, and to, for all the organizers for organizing this conference. So our journey today begins with the following theorem that can be found in Brighton and Hefliger's book. It's part of a theorem, like a mega theorem that takes up an entire page. And it says the following. So suppose one has a finitely generated group with a very well-behaved action on a complete cat-zero space. So for us, well-behaved will mean proper by semisimple isometries. So I should maybe explain what I mean by. So semisimple just means that the translation length is achieved by some point in the space. So an isometry is semisimple if the infimal distance that a point is moved by the isometry is achieved by some point in the space. So for example, any isometry of a Euclidean space is semisimple, and the same is true for isometries of trees, Euclidean buildings, finite dimensional cat-zero cube complexes. But for example, a parabolic isometry of the hyperbolic plane is not semisimple. It has translation length 0, but no point is fixed by such an isometry. But we like proper actions by semisimple isometries, and that's because if a finitely generated group has such an action on a complete cat-zero space, then it's well behaved from the perspective of non-positively curved groups. So for example, all polycyclic subgroups of such a group will be virtually abelian. Any finitely generated abelian subgroup of such a group is undistorted. And if any finite rank free abelian central subgroup of such a group is a virtual direct factor. So there's a finite index subgroup of gamma that contains H as a direct factor. And in fact, these statements are interrelated. For example, if H is a virtual direct factor, then H is undistorted because direct factors are undistorted. And a polycyclic subgroup, it's not difficult to see by induction that a polycyclic group that's not virtually abelian contains a distorted abelian subgroup. So we also have this implication. But basically the reason that these actions are so nice is that there's a flat torus theorem that's applicable to them. So here's the statement. Free abelian finite rank group acting properly by semisimple isometries on a complete cat-zero space preserves and acts as a lattice of translations on some isometrically embedded Euclidean space of the appropriate dimension in the complete cat-zero space. So let's give examples of groups that are nice in this sense. So for example, a group with a proper action on a cat-zero cube complex has all these properties because any isometry of on a finite dimensional cat-zero cube complex is semisimple. But also say any discrete subgroup of SLNC consisting entirely of diagonalizable matrices acts properly by semisimple isometries on this on the associated symmetric space. So a properness comes from discreteness, and an element of SLNC viewed as an isometry of the symmetric space is semisimple if and only if, as a matrix, the element is diagonalizable. However, more general finitely generated linear groups may not be as tame. For example, the three-dimensional integral Heisenberg group is linear, of course. We can think of it as a subgroup of SL3Z, let's say. And this is a polycyclic group that's not virtually abelian. In fact, it's a nilpotent group. And it's, I mean, one way to see that it's not virtually abelian is that it has a distorted cyclic subgroup. This subgroup is distorted. And not only is it, I mean, it's also central. In fact, the subgroup generated by this element is the center on the nose. And however, I mean, for example, because the cyclic subgroup is distorted, it's not a virtual direct factor. Here's another example. We can take this, so the group of subgroup of, say, GL2R generated by these two matrices is a copy of the Bamslag Solitar group BS12 sitting inside GL2R. And the cyclic subgroup generated by this element is in fact exponentially distorted. But something these two examples have in common is this abundance of unipotent elements, which brings me to this definition. So a square matrix is unipotent if it has the same characteristic polynomial as the identity, or equivalently if all its eigenvalues are 1, if 1 is the only eigenvalue of the matrix. So, I mean, an upper unitriangular matrix is, of course, unipotent, and a matrix is, in fact, unipotent if it's similar to such a matrix. And so, I mean, motivated by this observation in 2017, Button proved the following. So when I say a linear group is unipotent-free, I'll mean that it has no non-trivial unipotent elements. And Button showed that a unipotent-free finitely generated subgroup of SLNC has properties 1 through 3 over here. So here gamma need not be discrete and need not consist entirely of diagonalizable matrices. And one case of interest is that gamma, for example, lies in SUN, or one case of interest is that gamma is a finitely generated pre-compact subgroup of SLNC. In that case, it'll be conjugate into SUN. And then by Button's theorem, it'll have properties 1 through 3. So here I should really, the point here is that unitary matrices are diagonalizable, and a matrix that is diagonalizable, that is simultaneously diagonalizable and unipotent must be trivial, right? If 1 is the only eigenvalue and you're diagonalizable, then you're toast. But this begs the following question. does a unipotent-free finitely generated subgroup of SONC act properly by semisimple isometries on a complete cat0 space? As far as I know, this question is still open. But this brings me to recent work of my own, which at least gives, I mean, it doesn't answer this question on the nose, but it gives geometric reasons for properties 1 through 3 to hold for unipotent-free linear groups. So this is not a very precise statement, but here goes. So suppose suppose gamma is any finitely generated subgroup of SLNC. Then there is some action of gamma on a complete cat0 space X, possibly locally infinite. So here, when I say proper, I'll mean topologically proper. But such an action exists such that I mean, an action exists with the property that its restriction to unipotent-free subgroups is tame in the following sense. So if H is a unipotent-free subgroup of gamma, then first of all, I mean, the action of H, the subgroup H on X is proper. And then it sort of mimics an action by semisimple isometries. So if H, again, here I'm assuming that H is unipotent-free. If it is also free abelian of rank D, let's say, then it preserves and acts as a lattice of translations on a so-called thick D-dimensional flat in X. So really, I mean, yeah, I'm not going to define what that means unless someone asks me. You should think that it, I mean, so maybe I'll say that, for example, if a non-unipotent element of gamma will act with positive translation length on X. That's one. I mean, this is the case that H is isomorphic to Z. And finally, if one strengthens the conditions on H, one gets a stronger conclusion. So if H consists entirely of diagonalizable matrices, then in fact, the action of H on X is by semisimple isometries. So for example, this implies that any finitely generated subgroup of SUN acts properly by semisimple isometries on a complete cat0 space. So I'm not sure how much time I'm going to have, but I'm going to try to at least describe the action and maybe sketch the proof of one. But before I do that, I'll give an application. So let's build a 3-manifold as follows. Take a bunch of compact surfaces with boundary, and now take the product of those surfaces with a circle. So you get a 3-manifold with a bunch of torus boundary components. Here I haven't drawn the product with a circle. I've just drawn the product with an interval because that's, I mean, actually possible to draw. But you should think here that the inner surface has been identified with the outer surface. So these regions that these annuli that I've shaded here are actually tori. And now glue these tori by homeomorphisms of the torus. And what you get is a graph manifold. And here, I mean, I'm not saying, you can do this in, the dual graph here can be as complicated as you want it to be. Here it's pretty simple. But suppose you construct a manifold M like this, then the following holds. So so if you take, so if there is a finite dimensional C linear representation of the fundamental group of this manifold with the following property. For each torus subgroup, I mean, no non-trivial element of that subgroup gets mapped to a unipotent. Then one can construct a non-positively curved Riemannian metric on M. So a Riemannian metric on M with everywhere non-positive sectional curvature. And I mean, this is really a consequence of this thick flat or thick flat torus theorem. I mean, it's a consequence of property 2 here. Basically, I mean, it's a consequence of that and an argument of Lieb. So basically, once you know you have, if such a representation exists, then there's an action of the fundamental group on a complete cat-zero space such that these torus subgroups preserve thick flats and preserve and act nicely on thick flats in this space. And then that tells you that you can construct a non-positively curved metrics on each of the components here such that the induced metrics on the boundary tori are compatible with respect to these gluings. Okay. Okay, I think that's, well, okay, and maybe I'll say, so together with very deep work of several others, okay, well, okay, maybe I'll, so the, I mean, one obtains the following corollary. I'm really trying to emphasize that this should be viewed more as a corollary of the work of these authors, not mine. So I'll say exactly what they did and what I did. So one has the following characterization of when a compact aspherical 3-manifold admits a non-positively curved metric. That is true if and only if it's fundamental. I mean, if assuming M is compact and aspherical, it admits a non-positively curved metric if and only if its fundamental group embeds in a compact Lie group. And that's true if and only if its fundamental group can be realized as a subgroup of SLNC consisting entirely of diagonalizable matrices. And that's true if and only if its fundamental group can be realized as a unipotent-free subgroup of SLNC. I mean, what Su-Wise, I mean, what I should say, what Wise, Loop, Chitsky, Wise, Agel, and others showed is that if M is MPC, then its fundamental group is virtually special, and that gives us this implication. And now this is the Peter Weil theorem, really. This is completely obvious, and this is the direction to which I contributed. Okay, I have 5 minutes, so I'll just, not sure if I should, I think I'll just skip straight to the description of the action. So we start with some arbitrary finitely generated subgroup of SLNC, gamma. Since gamma is finitely generated, in fact, gamma is contained in SLNA for some finitely generated subdomain A of C. So this is Z adjoin finitely many things. That's what A is. And now let E be the smallest subfield of C containing A. So abstractly, this is the fraction field of A. And then E is some finitely generated subfield of C, and we can view it like this. So, I mean, we're interested in this sub-extension of E. That's just the algebraic closure of Q in E. And since E is finitely generated, F will in fact be a number field. It'll have finite degree over Q. Now, let O be the ring of integers of this number field, and let the sigma j be the d distinct embeddings of F into C. Because C is algebraically closed and has infinite transcendence degree over F just for cardinality reasons, we can extend sigma j to a map from E to C. And what's nice about these maps, sigma j, is that now if we embed E diagonally in you know, this product of C's via the sigma j, then this embedding will be discrete when restricted to O, when restricted to this subring. And now so that will sort of in fact, this would be enough if we knew that well, not exactly. Yeah, I take that back. So now a theorem of Alperin and Shalin comes to the rescue. So this is a result from 1982. There are finitely many discrete valuations on this field E, such that an element of A that lies in all the associated valuation rings is in fact an algebraic integer. So now, I mean, we have an embedding of A into this product via E, and that gives us an embedding of gamma into this product via SLNE. So here, this is the completion of E with respect to this valuation. It's not necessarily a local field, but it's some complete valued field. And so each of these has an associated symmetric space down here, and each of these has an associated, each of these has an associated Bruhat-Tietz building. And now the claim is that the action of gamma on this product of a finite product of symmetric spaces and buildings is the desired action. Briefly, I'll explain why, for example, when one restricts to unipotent-free subgroups, this action is proper. It's a very standard argument, actually. So all one really needs to show is that, so here B is some complex. Depending on your school, you maybe consider products of buildings to be buildings as well. But the point is, this is some complex, and what we want to show is that the stabilizer of a vertex here acts properly on this product of symmetric spaces. Well, why is that true? It's because of our assumption. I mean, we want to show that if, I mean, a unipotent-free subgroup has this property. So first of all, we notice that if, I mean, an element that fixes a vertex here will have to have the following property. All of its coefficients, all of the coefficients of its characteristic polynomial will have to be algebraic integers. And so we have this commutative diagram, and essentially because of discreteness of this map and continuity of this map, we know that any sequence of elements of this stabilizer that approaches 1 in this Lie group must be eventually unipotent. And then hence eventually trivial by our assumption that H is unipotent-free. Okay, thank you.
All right, thanks, Sami. Any questions?
Hey, can you hear me, Sami?
Yeah, yes.
Yeah, I have a question. So I'm wondering, okay, so the story began with, let's put it like that, very specific finitely generated groups that can act nicely on spaces. But now, when you are restricting to gamma to a finitely generated subgroup of SLNC, I'm wondering what can you say if instead of SLNC you just take a finitely generated subgroup of SLN or of an algebraic group over a global field? I mean, because the point is, and this could be in characteristic 0, but also in positive characteristic. The point is that the whole construction that you get here to cook up the action, you still get if you are picking a finitely generated subgroup of that lives in an algebraic group over a global field, right?
So you're asking, for example, if I had so if instead I was looking at finitely generated subgroups of this group, I would already have a very nice proper action. I mean, this strategy is in some sense supposed to generalize this. So I mean, your subgroup will lie in something that looks like this, and then this is some S arithmetic group, so it has a nice proper action with all the properties that I described just by virtue of lying inside this lattice. Really, and for fields of positive characteristic, the situation is even simpler. In fact, any finitely generated group that's linear in positive characteristic has an action. Proper action on a finite product of buildings. Really, the issue is transcendentals in the characteristic 0 case. That was the hurdle.
I see. Have you tried something with let's say Q? Let's say I don't know, Q let's say rational functions over Q or something similar. So we're still in characteristic 0, but at just one transcendence degree.
Well, I mean, this covers that.
Right. Yeah, of course. No,
so
sorry.
I mean, here for concreteness, I used C, but I mean, the point is that a finitely generated group that's linear over a field of characteristic 0 is linear over C.
Yeah. True. Yeah. Thanks.
All right. I think I'm gonna cut it here because we need to move on to the next talk in a minute. So thank you very much, Sami.